Okay, we have these problems. The first one is what exponential function would you invert to get the log base 4 function? Now remember, when you invert to get the log base 2 function, you do your basic 2 to the x function, right? Okay. Now some people are on track with this, but just to make sure everybody is, you invert or find the inverse of. I didn't want to write out all the words, but by invert, I mean find the inverse function of. Invert the 4 to the x function, okay? Just like you invert 2 to the x function, the basic exponential function to get your basic log base 2 logarithmic function. So, and we know how to do that. You know what to do with the table of the log base 2 of the basic exponential function 2 to the x function to get the log base 2 function. Okay. So we're saying, after a little bit of a get here, that we get the log base 3 graph by inverting the graph of the 3 to the x function. So three to the x functions, straightforward enough. And right here is a table for the log base 3 function. That's pretty much reviewed. I'm going to do this rather quickly, but I'm going to put A up here. Let me give myself a little more room. If I look over here, the lowest value I get here is -2, and all these values are positive. So my y-axis doesn't need to extend as far below the x-axis as it does above, because we need to go all the way up to 9 from the y-axis in order to accommodate 0.29. So I'm going to go on my axis like this. And the same thing occurs. Okay, let's just put it in standard notation. The domain of the 3 to the x function is 0 to 9. The domain of the log base 3 function is -2 to 2. So we just need to go from like -2 here up to, I'm going to go 8, and then we'll be able to figure out where 9 is. See how I did there. That would be 4. Here would be 2. Here would be 1. And then 1/2 and 1/4 here. Okay, so so 9 would be up about here. Okay. My domain, the domain of the 3 to the x function is -2 to 2, the usual domain, but the domain of the log base 3 function goes all the way out to 9. So I'm going to need to let's say put 8 out here, just because 8 is easier to cut in half than the 9. Once we got 8 subdivided, we see where 9 is. And then over here, we got to do 1/2 and 1/4. Now we have all the x values. for both functions, except we don't have -2 and -1. Well, there's x equals -2. Out here is x equals 2. Our values of 3 to the x are going to go from 1/9 over here at -2, 1/3 to 1 to 3, and then all the way up to 9. So our graph of y equals 3 to the x, it's a whole lot like the graph of y equals 2 to the x, but it goes a lot higher. Graph of y equals 2 to the x would only go out to the 0.24, where this goes all the way up to 9. The inverse function. Well, when x is 1/9, y is -2. Well, 1/9 is real close to 0, so we're going to have a point here very close to the y-axis, and 1/3 is pretty close to the y-axis. And then we got 1, 0, 3, 1. So out here is 3, here's 1. There's 3, 1, and then 9, 2. So 2 is here. 9, 2 is going to be like this. And everybody has a graph. Looks something like this. Now, if I want just a graph of y equals 3 to the x, I can use a little bigger, well, I can use a y scale. I'm sorry. See, okay. I may just say is, I want to look a little closer at the graph of y equals log 3x. I could expand my y-axis a little bit and get a graph that might be a little more accurate, a little more spread out, but we're just going to stick with this. Okay, so we want to sketch the graph now of y equals -2 log base 3 of x plus 1. So I think I'm going to redraw a graph of the log base 3x function. And I'm not going to use, I use more or less equal scales here. So this is kind of what they really look like. And your y equals x line is going to be here. And I didn't draw that quite well enough, but every point here is a reflection through the y equals x line. The point up there. The scales aren't quite equal, so I'm just going to draw the y right here. But this point reflects across from here. This point reflects across from here, and so forth. Those are all properties. I'm not going to belabor those right now. Those are all properties that the inverse function always has. Okay. Now let me quickly draw a graph of the log base 3 function, because really all I said was make a table, sketch a graph of this function. Wanted to reinforce of this graph and this graph compare. Let's just do now a graph of the log base 3 function without worrying too much about having equal scale. Okay, so now our point 1/9 -2, well, it's still going to be down here at -2, real close to the y-axis, closer than I made it there. 1/3, 1/3 -1, 1, 1, 3, 1. Okay. It's 1, 0, then 3, 1, 3 out here, 1 out here, and then 9, 2. Now let's use this graph and graph -2 log base 3 of x plus 1. So let's talk about this for just a second. What transformations are involved here, and what transformations are we going to want to do first? Okay, so we've got a really good quick answer here. To get -2 log base 3 of x plus 1, we reflect across the x-axis because of the negative sign, vertically stretch by factor 2. Now we can vertically stretch it and then reflect it, or we can reflect it then vertically stretch it. The -2 kind of does all of that, and it doesn't matter in which order, because it's both, the negative sign's a multiplier, so is the 2. So it's like multiplication before addition, order of operations. So we got to do the reflection and the stretch first, in either order, and then we vertically shift 1 unit. Well, I've got more room below the x-axis than I have above the x-axis, so I'm going to choose to reflect the graph first. And the reflection is easy enough. I just take this point down here and reflect it up here. This point here and reflect it up here. The point on the x-axis is its own reflection. Take this point and reflect it down here. Take this point and reflect it down here. So here I have then what I'm going to label this over here. Y equals -2 log base 3. Sorry. Be negative log base 3 of x, no -2 yet. And I've got to pop up on my screen. I can't see if I'm still on the board, but I think I am. Yep. Okay. And then I've got to vertically stretch now. So every point has to move twice as far from the x-axis on the same side of the x-axis, meaning that this point will go up to here, a little high. I'll go ahead and cheat, put it up here. This point will go up to here. This point will stay where it is. This point will go twice as far from the x-axis all the way down to negative. Okay, the y coordinate is, well, this point is 3, -1. There's our 3, 1 point that reflected down to 3, -1. So the y coordinate here is -1. When we do 2 times that, we're going to get -2. So it's going to go down here twice as far from the y-axis. And then this point will go twice as far from the y-axis. Since there's often a confusion between vertical stretch and vertical shift, I'm going to use two arrows of equal length to indicate that I've doubled the distance from the x-axis. And then I'll use 2 arrows of equal length here to show where this point goes. And now I have a graph. It's going to be up very close to the y-axis. And down here, very steep. And like so. All right. Now what do I have to do? I add 1, so I vertically shift 1 unit. So 1 unit is, so this is 1 unit here. So this point is vertically stretched down to here. Then I lift it up 1 unit, it goes back to where it came from. And there's my arrow of length 1, and I just apply that arrow to every point. And I find that I have a graph that is something very much like this. So this blue graph is y equals -2 log base 3 of x. Forward slash something negative sum down here. And this is y equals -2 log base 3 of x plus 1. Now, understanding all this can be very helpful in answering some of the open math questions where you identify a graph and see what the graph is. We'll make a couple of generalizations on this. But first, I'll go ahead and do the graph of y equals log base 3 of x minus 2, quantity minus 2. And I can kind of do that on the same set of coordinate axes. If you follow me here. Okay. I start with my log base 3 function, log base 3 of x. What does replacing x by x minus 2 do? Well, that horizontally shifts me 2 units. So this graph will shift 2 units over. So we'll shift over 2 units here. We'll shift over 2 units here. We'll shift over 2 units here. And we'll do the same here and here. So we have points that look like this. And we sketch a smooth curve. And this is y equals log base 3 of x minus 2. Just looking for a place to label this. Well, I'll label it in a minute. I want to draw my other graph. Make sure that I label it at a point or someplace where you can read it. So we've got y equals log base 3 of x minus 2 minus 2. That means every point of this graph is then going to shift 2 units downward. Now, 2 units downward, 2 units is bigger on the y scale than it is on the x scale. So this point's going to go down 2 units. This point's going to go down 2 units. And this point will go down 2 units. And it's going to be a little clumsy to draw that, so I'm actually not drawing it. This point will come down to here, and this point will come down a little lower. I see that our graph is going to look like this. Looks like this. So here's graph of the log base 3 of x minus 2, not log base 3 of x minus 2 minus 2, not x minus 3. And here's my log base 3 of x minus 2. Another thing about this horizontally shifted graph, both of these horizontally shifted graphs, the y-axis also shifts over 2 units. It gives you the asymptote, vertical asymptote. So there's 4 there. So I'm going to have a vertical asymptote. Different colors so you can distinguish it. X equals 2 is your vertical asymptote. both of the horizontally shifted graphs that we constructed. Because when you horizontally shift the graph 2 units, everything shifts 2 units to the right, including the vertical asymptotes, including the vertical asymptotes. So the vertical asymptote of the log function was the y-axis. Vertical asymptote of both of these is a line x equals 2. The y-axis shifted over 2 units. And there's one property. So when you see a graph of a logarithmic function on a scale, and so open math might show you a graph that looks like this. With a logarithmic, basic shape of a logarithmic graph, maybe like this, maybe like one of these. You can identify the horizontal shift immediately if you can identify the vertical asymptote. So, see that your vertical asymptote might be here. Here's your vertical asymptote. Here's your horizontal shift. I think we just bored over a little bit. Okay. So right here's our horizontal shift. We didn't do the horizontal compression, so I'm going to kind of leave that to you to reason out. You have examples in the open math, but basically, if the distance between your vertical axis and your x-intercept is 1, then you don't have a horizontal compression. And I don't think that open math does a whole lot with horizontal compression, because I could be wrong, but I don't remember seeing anything of that nature. And I'm always inclined to keep the transformation simple and not talk too much about horizontal compression, except with the case of exponential functions. So I'm not going to talk about it here. If it becomes necessary, please let me know, but I don't recall having seen or chosen problems that involve horizontal compression. Okay. The other thing, though, is how do you identify that this is a log base 3? As opposed, or, what's the base of the logarithm? Okay, well, if this distance is 1, then this distance will be 1. And the value of the function here comes from, well, let's back up. Let's contrast the log base 2 and the log base 3 functions. For the log base 3 function, when x equals the base, y equals 1. Because the base raised to the first power is the base. In other words, go back to the basic function is 3 to the x. If you plug in x equals 1, you get x equals 3. Right there's your base. So here's your base, here's your base, and here's your base. So when x is equal to the base, y equals 1. Now, if you shift the graph, if it hasn't been vertically stretched or reflected, this will be your base. So if this distance is 1, and this distance is 1, right here is your base. I don't want to go too deep into this because the examples you're given in open math are all fairly obvious, okay? And they're all done on a grid, so you can see where the points go, you're given some multiple choice and so forth. So got a log function, low vertical stretch. You can kind of use this as a guideline. The main thing I'm going to want you to do is be able to graph these things. You recognize when you have a graph of a logarithmic function. Let's just take the idea that if you know how to do the graphing, then you know where these graphs that you're asked to match up are coming from, and it reinforces the whole application of transformations, which I consider to be the most important thing. So, bottom line, know how to graph them, and the open math examples show you examples of transformed functions. You'd have to figure out what the transformations are, and then you know what to do with the function. Okay. I'd like to say more. I'd like to do more. I'd like to draw these on a grid, but we're trying to stay ahead of the pre-calculus class, and we're going to need to move on. And, okay. Okay, so I'm not going to write it out, although in pre-calculus class I might well write it out because we're more or less at the same place in both classes. But the 5 is going to be your base, and the x is going to be your exponent, and the 7 is going to be what it's equal to. And that becomes, well, it becomes log base becomes log base 5, and log base 5 of what equals a, which is your exponent. So the base and the exponent are the easiest things to recognize. If I recognize it correctly. Okay, the base and the exponent go here and here, because there's your base and there's your exponent. So I don't know what's going on. Brain isn't totally functioning yet. But my problem is I got a good night's sleep. And usually if you get a good night's sleep, it's because something weird's going on. So I'm a little, I don't know, a little bit strange today, but I know what I'm talking about. The words don't want to come out right. Okay, that happens sometimes, and I apologize for it. Okay, and obvious connections. Anyhow, there we got it. Okay, so we got log base 5 of 7 equals x, and that's what everybody got. Again, you can easily recognize your base, which goes here, and your exponent, which goes here. And if you really know what the base is and what the exponent is, that's what you get. And then the thing it's equal to goes here. Okay. Now let's just digress a little bit. This isn't one I asked for, but what if you have four times 5 to the x equals 18? What are you going to do with this? Just Gonna pause for a second. Okay, so the problem with this equation is this equation is not in this form. This is just a plain old bare b to the a equals c. Well, you got a b to the a, but you got something in front of it. You got that 4. It's multiplied by 4. So it's not in that form. So what can you do to the equation to get the form? Well, we divide both sides by 4 to get. So it's 18 over 4. I'm going to say it's 9 halves. Okay. So again, I haven't written out the steps. If we divide both sides by 4, we do get a 5 to the x here. We get 18 fourths, which reduces to 9 halves. So now we convert the form and we get log base 5 of 9 halves equals x. And then what's the next step in the solution? X is a log of 9 halves divided by a log of 5. One of your rules, and a pretty easy one to remember. And to actually calculate it, you can't count. This is your exact solution. And your calculator can approximate it because you have a log key on your calculator. So the basic conversion is always easy, but you do have to get the equation into the form where you can convert it. Okay, well then, log of 1/3 of x equals 9 becomes 1/3 to the 9th equals x. Okay. And 3 to the 9th power, 27, 81, 343 is 5, and 81. Going to be up in the $200,000 range. And this is not a good day for me to try and do mental arithmetic. Usually you can do that power. It's going to be like 0.0004 something, I think. But today that's even more unreliable than usual. Okay, so easy to solve. 3 to the 2x minus 5 equals 8 becomes log base 3 of 8 equals 2x minus 5. Now we can go on, I didn't ask you to, just ask you to convert, but once we converted, it's easy to solve this, but it gets a little weird because you don't have a number for log base 3 of 8, and you don't want to use a number for log base 3 of 8, because the only number you could write for log base 3 of 8 would be an approximation. Because log base 3 of 8 is an irrational number, just decimal expansion just keeps going and going. We don't want to use round offs, then we need to just treat log base 3 of 8 just like any other symbol. So we can say that, okay, 2x minus 5 is log base 3 of 8. So 2x we add both 5 to both sides, we get 2x equals this. So x equals log base 3 of 8 plus 5 over 2. That's your exact solution. And now we approximate it. As appropriate. Make an appropriate approximation if we need an approximate solution. Let's try this out. We're actually going to be able to solve this equation log base 8 of x squared minus 5x plus 6 equals 2. Convert it becomes 8 to the second equals x squared minus 5x plus 6. Well, that's easy to solve. Just use the quadratic formula. Now we expand it, we get x squared minus 5x plus 6 equals 64. Put it into the standard form of the quadratic. And etc. using quadratic formula. So you give me an exact solution, you can approximate it using the quadratic formula. I think I'm going to stick my neck out. We're going to get x equals 5 plus or minus the square root of. You're going to get 25 here. You're going to get 4 times 58 there, which is 232. So you're going to get 257. Put a little question mark over here, a little question mark over here, because I did that calculation in my head. But that was a pretty easy one. I almost trust my head. Okay.